All right, hello everyone. It's time for exam 4. Yeah, exam 4, I think. Or is this 3? I'm losing track. No, it's exam 4. Exam 4 review. Woo! Yeah, I know we're all excited for exam 4. There are a lot of exams in this class, and I understand it seems like a lot at a time. But on the bright side, at least you cover only like 1 or 2 chapters per test rather than 4 chapters for a single test. So at least there's that. All right. So today we are going to be starting with the idea of alkenes and the whole idea of what we can do with alkenes. So if you recall, in the previous chapters, to actually make an alkene, what we've done is we've done is sort of an elimination reaction. This could be E1, E2. We can make the Zaitsev or the Hoffman product. All that really sort of matters to us right now is this is how we make an alkene. We do elimination. That should be an L. Sorry. So this is going to be elimination to create an alkene. But why would we want an alkene to begin with? Well, after we get those alkenes, we can do a bunch of different reactions with them. Notably, we will be doing addition reactions with them. And the definition of addition reactions, as far as organic chemistry goes, is we start with a pi bond and we remove that pi bond to create 2 new sigma bonds. So sigma bond X and sigma bond Y. These are just placeholders for whatever we're adding. Or over here with this terminal alkene, we'd go sigma bond X, sigma bond Y. It just depends on what kind of reaction we're doing, what we want in the end, etc., etc. And something to note here is X and Y can be added in different ways. They can either be added to the same side. So what that means is they're added as both wedges or both dashed wedges. I'm going to just use this XY on the left so I have a little bit more room to draw. So again, they can either be added both on solid wedges or dashed wedges. So both X and Y are solid wedges, or X and Y being both dashed wedges. That means that X and Y are added to the same exact side, so we're going to call this syn addition, S meaning same. Another outcome for this is they're added to opposite sides. So X can be a dashed wedge or a solid wedge, and Y will be a dashed wedge, and vice versa. Now they're added to opposite sides. And so the word that we use for opposite is going to be anti. So we have syn addition and anti addition. Addition is when we go from a pi bond to 2 sigma bonds. Syn addition is when that addition happens to put the X and the Y, whatever we're adding, on the same side of our compound. And anti addition is when we add them to opposite sides of our compounds. And you'll see why syn or anti is the outcome depending on what kind of reaction that will do. But again, I just want to make this terminology clear before we continue on. Yeah, so that's syn and anti addition, just in general. All right, and I'm planning on doing the naming stuff sort of at the end of each chapter because I feel like knowing how the reactions work is a little bit more important than knowing how to name them, because I feel like naming them is something that's just a smidgen easier, and I feel like most people are going to stay for the beginning and sort of peter out the ends. And I want to give you the most important information at the beginning. Okay, so now let's go over the types of additions. So of course, we're going to start with our alkene, and there are a few different types of additions that we can do. One type of addition sort of adds a hydrogen first, and then it adds a halogen after the fact. This is called hydrohalogenation. And organic chemists, they name things for a reason. So we can see here that hydro means we're adding a hydrogen, halogen means we're adding a halogen, and nation just means this is happening. So we can also look at this name to see the order that things are added. So hydrogen is added first. So the way that happens is these pi bonds that are making up this bond, this double bond right here, are going to go out and they're going to grab the hydrogen from some sort of HX, so like HBr, HCl, HI. One thing to note is that we're usually not going to see a reaction like this with HF. Why is that? Because if you recall from our acid base chapter, F is sort of a bad conjugate base, which makes it super, super, super unstable on its own. And as a result, it won't really want to lose its hydrogen as easily as stuff like bromine, chlorine, iodine. So most of the time, you're not going to see HF in these reactions for that reason. All right. So we can see here that our electrons are attacking a hydrogen. Hydrogen can only hold a single bond, aka 2 electrons, so whatever bond it's attached to has to break. So let's pause for a second. We can see here that pi electrons are attacking a nucleus. So right now we are considering our pi bond here, our alkene, as a nucleophile because it's using its electrons to attract a nucleus. Okay? And then what do we end up with? Well, we add a hydrogen to one end of the double bond, and the other carbon that was part of that double bond will gain a positive charge. And this may not be as clear just looking at the line angle structure, so let's quickly sort of dive into the Lewis structure for this. So if we look at the general Lewis structure for a carbon-carbon double bond, we can see that each carbon has 4 bonds total, and 2 of those bonds are taken up by that double bond. If one of these bonds, 2 of those electrons, goes out and grabs a hydrogen, that means that that bond is going to break. And so then what that means is that hydrogen will have to go to either one carbon or the other. Let's say it goes to this carbon. So now this carbon keeps its 4 bonds. However, this carbon on the right lost one of its bonds and it did not gain any more electrons. This means that that carbon is going to gain a positive formal charge. And if we do the whole formal charge equation, carbon has 4 valence electrons on its own, minus 3 bonds, minus 0 electrons in lone pairs, that equals plus 1, and that's where that positive charge comes from. Okay? And so then what happens is our halogen from before, in this case Br, is going to come in, and now the Br is going to act like the nucleophile. And then it's going to attack that positive charge, and now we're going to end up with our final product, HBr. So let's pause for a second and let's just look at this. This sequence here should be kind of similar to you. It should be kind of similar to you because it's very, very similar to the idea of SN1, where we make a carbocation, which is then attacked by a nucleophile, and we end up with an alkyl halide. So we can see here that this is very similar to SN1. So many of its properties are also going to be similar to SN1. The first property we're going to talk about is going to be the carbocation. So one carbocation. So obviously, just like in SN1, we are going to want to form the most stable carbocation. And remember from last chapter or the chapter before, the more substituted our carbon is, the more stable it is. So tertiary is more reactive than secondary, better than primary, etc., etc. So what this means is the hydrogen is going to attack the opposite carbon to the one that will form the more stable positive charge. So if we look at an example that looks like this, we can see here, okay, there are 2 possibilities that the hydrogen can attack. They can attack at carbon 1 or they can attack at carbon 2. If we attack at carbon 1, we end up with a hydrogen right here and our positive charge right here. We have a tertiary carbocation. If we attack at carbon 2, we'll end up with a hydrogen right here and our positive charge right here. We can see that that is a secondary carbocation. Obviously, the tertiary carbocation is more stable than the secondary carbocation, so that's the one we are primarily going to make. And yes, it is possible to make this carbocation. It's just in such minuscule amounts that we sort of don't consider it when we're doing these reactions. So just think of the more stable carbocation will be the one that we form. And we can also note to ourselves that the carbon that the hydrogen is going to attack will be the one that is less substituted, because of course we want the positive charge to go on the more substituted carbon. This is the idea of Markovnikov addition. So Markovnikov, spelled like this, hopefully. I'm not great at spelling. I have a math and science brain. And you'll probably see me referencing this as Mark because it's faster to say. So the idea of Markovnikov addition is that hydrogens will add to the less substituted carbon, aka the carbon with more hydrogens. Because if we look at carbon 1 in our example here, we can say that, well, carbon 1 is still going to have 3 bonds. It's just its last bond is taken up by a hydrogen. The hydrogen wants to be with other hydrogens, so then it adds to carbon 1, making that have 4 bonds and putting the positive charge on the more stable carbon of the two. Okay? So that's the idea of Markovnikov. Hydrogen adds to a less substituted carbon, and then the other thing, in this case, our halogen, will add to the carbocation, the more substituted carbon. Okay? All right, so let me erase this here. I'll move that word over here. So it's going to be Mark. All right. The second thing we're going to have to sort of think about as far as this addition reaction in comparison to SN1 is the stereochemistry. So if you remember, as far as the stereochemistry, as far as SN1 goes, this nucleophile, it can add either side. It can add as a solid wedge or a dashed wedge. So that means we'll end up with this plus this. And we can also imagine that, oh, the hydrogen was added on either a dash wedge or a solid wedge. It doesn't really matter, at least not in this case, as long as the hydrogen is going to be the same type of wedge on each sort of different possibility. So we can see here that we have one that has the H and the B are on the same side, and one where H and B are on opposite sides. So we can see here that as far as hydrohalogenation, it will add both syn and anti because of the carbocation intermediate. Because again, the hydrogen will add as either a solid or a dashed wedge, and it'll just stay like that. The bromine will add as a solid or a dashed wedge, and then we can compare that to the hydrogen that we added, and that will either be syn or anti. They're generally added in the same sort of, they're generally created in the same equivalents. So there's about the same amount of the syn product as there is the anti product. Okay? All right. Does that make sense to everybody so far? All right. Okay, awesome. So that was hydrohalogenation. And I hope that made a lot more sense for you guys. And so the next thing that we're going to be talking about, somebody says it doesn't really matter because we don't keep the hydrogen anyway. The hydrogen doesn't have to be written. Yes. So like we wouldn't have to write the hydrogen here. What's important is that the Br is both a solid and the dashed wedge. The words syn and anti are sort of the words syn and anti, they do refer to what we're actually adding. So when we say syn and anti products, that means we add one where both hydrogen and bromine are added to the same side. Oops, I wrote bromine again there. And anti, one where hydrogen and bromine are added to opposite sides. They're just made in equal amounts, and it's faster to just draw one sort of pair of them rather than drawing all 4 possibilities. Like here's another possibility here where we do this one, and then we do this one. These two products I drew here, they're basically equivalent to these products here. They're just at a different perspective. And somebody asked, could you have switched the H and the Br? In this case, yes, because both carbons of the double bond were equivalent. So both of them were secondary. And in this case, we would form a race-make mixture because we only have one stereogenic center. The exception to this is if the carbon that we add to, so like this one here that we add the hydrogen to, if that was also a stereogenic center, then instead of making enantiomers, we would make diastereomers. Somebody said, why can't the Br go on the other carbon than the top carbon? Oh yeah, it doesn't really matter as far as this top problem went, which carbon we add the hydrogen to and which carbon we add the bromine to. I just used this one as an example because I didn't have to follow Markovnikov rules before I explained it. We'll do a few more practice problems in a bit. I'm just gonna move on to the next problem if everybody is good with this. Would you get 4 products with 2 chiral centers? Yes. Aren't these 2 products technically diastereomers? Good eye, but not quite. That is if they are enantiomers because we can see here that this guy here, this has another hydrogen attached to it. So that would make this center here not a center. So that carbon is not a chiral center. So we only have the single chiral center with the bromine, where they're opposite, making them enantiomers. Okay? All right. And if you had 2 chiral centers, yes, you would get 4 products. All right. All right, we good? All right, I'm going to clear my screen and we'll move on. So we're going to do something similar to all of that. We're going to do something called hydration. So I'll put hyd using an acid. Again, organic chemists sort of name things purposefully. So hydration means we're adding H2O. We may add hydrogens and oxygens to different carbons, but overall, we are going to be adding an H2O to our alkene. Using an acid means we're using an H plus ion. And this acid could be H2SO4, HNO3, H3O plus, anything really. The one that you're going to see the most, however, and you're going to see the one that I use the most, is going to be H2SO4. And you're going to see me draw it in sort of a peculiar way. I'm going to draw it like this, HSO3, HOSO3H. And the reason why I draw it like this is because this is sort of the pseudo Lewis structure, because the Lewis structure looks like this. And I want to draw it in a way that I can draw the mechanism with this hydrogen right here, so it's exposed and everything. And I don't want to draw the full Lewis structure because I'm lazy, so I kind of draw this sort of pseudo Lewis structure, okay? So H2SO4 and H-OSO3H, they're the same thing. It's just HOSO3H is a lot easier to draw the mechanisms with, okay? All right, so let's erase this really quickly. And as far as the acid goes here, I'm just going to use H plus to show that any acid could technically work. So let's use the same, let's use this one here. So now we can actually do Markovnikov, okay? So the first thing that happens is our acid is going to add a hydrogen to our alkene. Again, the alkene is acting as a nucleophile using its pi electrons in order to grab a hydrogen. And so then what happens? Well, we are going to add Markovnikov because again, we're going to want to put our positive charge on the most substituted carbon, aka putting our hydrogen on the less substituted carbon. Okay? The next thing that happens is we are going to add water. So I'm going to write HOH here and then draw our line here. And we end up with this here. And of course, we are going to want to deprotonate that oxygen, just like we would in SN1. And usually what you'll see happen is the conjugate base from our acid is going to come in and grab that hydrogen. So I'm going to put a conjugate base, CB here, grabbing the hydrogen, this bond breaking, and we end up with our final, oops, that's purple, not black, and we end up with our final alcohol. And you may be saying, Casey, you told me we're adding H2O. Where's the H2O here? Well, the other H we added counts in this case. So in total, we added H2O. Okay? And if we pause for a second and we just look at this portion right here, we can see, oh, it's the same mechanism as SN1 again. It's just the big difference is, same with hydrohalogenation, is instead of having a leaving group leave, we added a hydrogen instead. Okay? Does that all make sense to everybody? All right. And the same concept will happen here as far as Markovnikov because of our positively charged intermediate, our carbocation intermediate. And again, as far as syn versus anti goes, this will be both syn and anti because I spelled anti wrong. Conjugate base. CB stands for conjugate base. So this will be syn and anti for the final product because again we have that carbocation, which means our nucleophile over here can either add as a dash wedge or a solid wedge. Okay, so again this is very similar to hydrohalogenation. We're just using slightly different reagents. Okay. So those two are the main two that will add syn and anti because those two have the carbocation intermediate. Now we're going to get into something with a slightly different intermediate. Somebody said, will this follow the same rule of producing enantiomers? Yes, exactly. So in this case, we didn't have any stereogenic centers, but if, for example, this OH was on a stereogenic center and this H was not, then we'd form enantiomers. If the hydrogen and the OH were on separate chiral centers, then we would form diastereomers. Somebody said, can you have syn and anti? Yes, this one has syn and anti. All right, I'm going to go over the reagents really quickly for hydrohalogenation and hydration using an acid. So if a carbocation intermediate is formed, there is syn and anti. Exactly. That's exactly it. Because of the carbocation intermediate, we form syn and anti. So if you see that carbocation intermediate, syn and anti will be formed. Okay? So let's go over these two just one more time. So hydrohalogenation, I'll just call that HH, and hydration using an acid, I'll call that HA. Hydrohalogenation uses HX, where X is any halogen as far as Cl, Br, and I goes. Remember, we don't use F because it's a really, really bad leaving group. It doesn't really, or F is a bad leaving group and it won't really react because it doesn't want to lose its hydrogen. Hydration using an acid, we'll use H2O plus some sort of acid. Okay, and a lot of the times you're going to see this acid be H2SO4 or H3O plus or even just H plus. But again, I personally are going to use H2SO4 the most. Okay, and somebody is asking about carbocation rearrangement, and I'm going to put a pin in that. So like over here, carbocation rearrangement. Because yes, both hydrohalogenation and hydration using an acid can undergo carbocation rearrangement. And just as a refresher, what this means is if we have, like for example, if we start with this type of double bond and we add our initial hydrogen, and we put our positive charge right here, since we have a more substituted carbon next to it that will make a more stable carbocation, will undergo some sort of shift. In this case, a hydride shift where the hydrogen will move, and as a result, the positive charge will also move. Okay? So yes, both hydrohalogenation and hydration using an acid can undergo this carbocation rearrangement. Sometimes we don't want that to happen though, and that's where some of these other reactions come into play, such as oxymercuration demercuration, which we'll get into a little bit later. Okay? Does that all make sense to everybody? And again, if you ever have a carbocation, you can undergo rearrangement. So that's something that you always have to look out for. How are the reagents written in the problem? would acid catalyzed have H2 on the top and acid in the bottom? So a lot of the times what you'll see is, so let me clear this. So let's say we have our alkene here. So we have our alkene here, and we're going to be doing hydrohalogenation. Usually what will happen is the reagents written on the top of the arrow is what's actually reacting with our carbon carbohydrate. So in this case, as far as hydrohalogenation goes, the HX directly reacts with our alkene, so we're going to put that on top of the arrow. As far as hydration using an acid, we're going to put H2O on top of the arrow. Why? Because that is what's mostly going to be reacting with the alkene. We're going to put our acid on the bottom. So for example, you might see H2SO4 on the bottom because the H2SO4, our acid, is going to be known as an acid catalyst, because we start with our acid and we should also end with our acid. Because remember, that acid is going to give its hydrogen in the very beginning, but at the end, what's going to happen is it in its conjugate base form, so for example, HSO4 negative, will reclaim a hydrogen because we have to do deprotonation, and we end up with the same acid that we started with. So catalysts, solvents, those are generally, as a general rule for Orgo 1, those will be on the bottom of the arrow. Okay? All right, perfect. So those were the two reactions that have carbocation intermediates. So those are the two reactions that will have both syn and anti-addition. Okay? So now let's get into the just anti-addition. And this is going to have to do with halogenation and halohydrin formation. And we'll get into both of these. We'll do halogenation first. So halogenation, again, is exactly what it sounds like. We're adding halogens. So what that means is we're going to use X2, where X is BrCl I. So we could have Br2, Cl2, or I2. Any of these will work. Most of the time, generally, you're going to see Br and Cl more often than I, and that's just because I is a good leaving group, so a lot of scientists won't really bother writing with it, and so that's why you'll see me interchange between Br and Cl, but I won't often use I. I still can be used, but you just won't see me writing it too often. Okay? All right. So again, halogenation is exactly what it sounds like. We're going to be ending it. We're going to start with our alkene, and then we'll end up with two halogens added to either side of that alkene using X2. So now let's get into the actual mechanism of this. So this mechanism is always confusing the first time you see it. So I'm just going to sort of write it out, and then we'll talk about what's actually happening here. So let's write out the first step of this mechanism. Again, the double bond will act as a nucleophile and grab onto whatever we're adding. But what's also important to note is that the Br, or whatever halogen we're using, will also act as a nucleophile and attack the other carbon. And we'll get into why that is in 1 second. And again, this bond has to break. And so now we create our intermediate. This intermediate is called a bridged halonium ion intermediate, or just a bridged halonium intermediate. Both of those names are technically correct. You'll probably see bridged halonium ion intermediate used more in this class because it's technically more correct. So when I say bridged, hopefully I spell everything right, halonium ion intermediate. What all of this means is we have a bridged section. That means one carbon is sort of linked to another carbon through the same atom. That's what the bridge is. This here is our bridge. Halonium ion means that we have a halogen that is charged. Of course, halogens with two bonds and two lone pairs, which is the case here, will be positively charged with its formal charge. Intermediate, that just means this is an intermediate of our reaction. So let's pause and talk a little bit about why this intermediate is formed. And I'll show you sort of what if this intermediate wasn't formed, and what if we formed the carbocation instead. So if we form the carbocation instead, we would have a Br up here and a positive charge right here. Now, remember something about this Br carbon bond. That bromine is very electronegative, so it's going to pull a negative charge towards itself, and now this carbon will be partially positive. And so what's happening here is we cannot have this structure. Why? Because this partially negative bromine is really attracted to that positive charge of that carbon. And so what instead forms? This bridged halonium ion intermediate. That is why this whole thing is formed. Whereas a lot of the times you're like, well, why is it formed? It looks so unstable. Well, it's because it's more stable than the carbocation intermediate, because we have that negatively charged bromine that's highly, highly, highly attracted to that positive carbocation. So that is why the bridged halonium ion intermediate forms. And so let's talk a little bit more about the actual stereochemistry of this intermediate. So a bridge, I don't know if you've ever been on a bridge, but usually a bridge is sort of straight. Your bridge doesn't like twist around a bunch. And with that in mind, we're going to put our bridge head, our bromine, our halogen, or whatever, on the same type of wedge, whether it be a dashed wedge or a solid wedge. And this is because we don't like twisting bridges because those will collapse very easily. So we're going to have them both on the same side rather than having them one solid, one dashed. Another way you may seen this drawn is instead of giving the bromine the wedges, you might give these legs the wedges. So like you might make these legs the same wedge. It doesn't matter as much that you make the legs the same wedge, but it does make things a little bit easier as far as the stereochemistry at the end goes. So I'm going to tell you, most of the time, use this version where we put the bromine on the whatever wedge we're using, because that will make things way, way, way easier. Okay? All right. So does everybody understand the bridged halonium ion intermediate now? I'm going to erase this one and replace it with the one that I drew with the stereochemistry. Okay, because I know the bridged halonium ion intermediate, it confuses everyone. Everyone the first time they see it. It confused me so much the first time I saw it. So I do my best to sort of break it down for everybody. Okay? So the next part of this whole equation here is oops, that is the wrong color. The intermediate is now going to be attacked by our remaining bromine. Okay? And so what's generally going to happen is this is going to leave and the bromine is going to attack. This is sort of analogous to SN2 because our leaving group is leaving at the same time as our nucleophile, which is what this is attacking. So as a result, we're going to end up with inverted stereochemistry at that carbon. Okay? This stereochemistry at this carbon will stay the same. You can think of it as I'm only cutting this rope. So this rope is going to stay exactly the same. So then what happens is we end up with something that looks like this. So we can see here that the two bromines were added on opposite sides. If you recall, that means this is going to be anti-addition. Okay? You may also see anti-addition added like this. They're both the same thing. Yes, it is exactly like a backside attack. Because this is really, really similar to an SN2 reaction. So just like an SN2 reaction, our nucleophile will do a backside attack because this slightly negative bromine is going to push that bromine, the other nucleophile, to the back. Because again, remember when we talked about SN2, our leaving group pushes our nucleophile to the back because they're sort of fighting for space. Okay? Does that all make sense? Could you put both bromines on the wedge? If I put both bromines on the same wedge, so like this, that would be syn addition. Syn addition does not happen in this case because, again, we're doing something similar to SN2. So that means we're going to have to do a backside attack and make an anti-product. And yes, this would produce two products if we had two chiral centers. So yes. So in this case, two different products because they're two chiral centers. Do you think that these are enantiomers or diastereomers? Oh, they are enantiomers. I answered that really, really quickly. But anyways, they're enantiomers because these are technically mirror images of each other. Like if we held up a mirror to right here and we mirrored them this way, they will be mirror images and they're non-superimposable. And if we did have a meso compound, then we wouldn't form then we would form one product. Sorry, I misspoke there. But meso compounds generally aren't formed in these cases just because, again, we're doing anti-addition, and meso compounds are defined by their line of symmetry. And when we add anti, generally we aren't creating a line of symmetry. Okay? Does that all make sense to everybody? Okay, awesome. I'm glad I could help. One thing that you may see in the book that is a pretty intense thing to sort of hit you with is sometimes they'll show this. Oh, well, this is the anti-product, and it is. And you may be saying, Casey, what the heck? That they're both on the same wedge. How is this anti? Well, it's anti because what we did here is essentially we took this first product right here and we rotated this bond around to put this bromine on the solid wedge. It's the same concept as when we had this guy right here and we picked him up by his head and we spun him around in order to put our different priorities on different types of wedges. This is the same type of thing, and I'll draw that out in a second. And yes, it's sort of because these directions are different, which makes it anti. Yes, we will go over reagents, syn and anti in a list form to summarize everything. I'm just teaching you them one by one before hitting you with that list. All right. So let's go over really, really quickly why this product is actually anti. So if we take this guy here, let's take this end right here, and we redraw him so we have our things straight up and down like this. Oh dear, I hope I can draw this well. Um, Br. Here is a hydrogen because the hydrogen isn't drawn in. Here is our regular line here, which is just CH3. And then up here we have CH2, Br, etc., etc. So CH2, Br, etc. So essentially what we do when we do this type of question is we're going to pick up this thing. We're going to pick it up by this end, and we're going to twist him around. So Br goes on the dashed wedge, H goes on the solid wedge, or the regular wedge, and then the CH3 goes on that wedge, and we end up with this here. So CH3 here. I'm reading the chat while I do this, so I'm going a little bit slow. So going off of that, we should expect to see our answers in two different forms. You should be able to recognize the anti and the syn product uh, in different types of forms, if that makes sense. I hope that made sense a little bit. Okay, awesome. So, anyways, back to this. What was I doing? I was showing you how this is like a twisted around version of this. BR, here. And so now we have Br on the dash wedge and CH3 on the solid wedge. So let's draw that. So if we go like this, hydrogen, CH3, Br, Br. So I'm getting a little bit off track because this is getting, so if it's in a cis-syn form but on a wedge, we can just rotate it, be trans-anti. It's sort of like the idea of, let's say that we have two different blocks. We have a block where we have like a play block here, like a. Oh God, that is not a cube. Please forgive me. We have a cube where Br is on this side, and then it's connected to a cube where Br is on the other side. So like Br is over here. But they're connected by a string, which means it's okay to twist this guy around and put our Br on the front on this other one here. I'm getting better at drawing those cubes, I swear. So you can see here we didn't change the actual blocks. The blocks are exactly the same as they were before. It's just we twisted around this string in order to put Br at the front. So it's just rotating it to turn it into from this form into this form. Okay, does that make sense? It might be going over your head. It would help a lot more if I could show you like a three-dimensional structure, but that's kind of hard in this 2D space. But I hope that helped you understand why this is actually considered the anti-product, because when we twist things around, it comes from this. All right. So it'll be, yes, it's sin if the dashes and the wedges are on the same side. So like for example, this is sin, so like x. This is also sin, because both of these versions are the same thing. It's just one is twisted around. Okay? Does that all make sense to everybody? Okay, awesome. All right, so that was halogenation. Now we're going to get into halohydrin formation. And halohydrin formation is basically the same thing that we just did, but now we're going to be using a slightly different set of reagents. So the first step is going to be the same. We start with our halogen. Oh, let me break down this name really quickly. Halo means halogen. So halogen. Hydrin means a hydroxy group, which means an OH group. Okay? So first thing we do, we make our bridged halonium ion intermediates, just like before, for the same reasons. Okay? And then what happens is we're going to use water, so like OH2, to do the SN2 reaction. And the reason why it can do this SN2 reaction, even though it's a weak nucleophile, is because this bromine, this bridge halonium ion, it's very, very strained. So it's going to take any nucleophile it can get to do an SN2 reaction. But it still is going to be doing that same sort of pseudo SN2. And so we're still going to end up with anti-products because, again, whenever we do SN2, we're going to want to do the backside attack. And again, this OH2 is protonated, so we're going to deprotonate it using this Br from the beginning. So if you remember, we only use one of these bromines to make that bridge. So we have a free bromine with a negative charge sort of floating around. And so what it's going to do, grab the hydrogen, break this bond here, and we end up with our halohydrin. And again, the halohydrin will be anti because we have the bridged halonium ion intermediate. So again, just to reiterate, you're syn and anti when you have a carbocation intermediate. You're only anti when you're a bridged halonium ion intermediate. Okay, so that's how we tell if something's going to be syn or anti, just by looking at the intermediates. Okay, does that make sense to everybody? If we differentiate halohydrin and halogen with the reagents that we have on it. So halohydrin formation, it's going to have X2 and H2O. Halogenation will only have X2. So just one more, I'm just going to go over it one more time. We're going to do syn and anti when we have a carbocation intermediate. We're going to do only anti when we have a bridged halonium ion intermediate. Okay? Does that make sense to everybody? All right, perfect. All right. Okay, so let's go over the halohydrin just one more time, just to go over the mechanism just very quickly. So we'll have our alkene, and then we'll have Br, Oh, one more thing before we move on. We did not talk about Markovnikov addition as far as halogenation went. That is because it didn't really matter too much because we were just adding two of the same thing. But now what we're doing when we do halohydrin formation, we are going to be adding two different things. So now we sort of have to take into account the Markovnikov rule. Okay, so the idea of the Markovnikov rule, it's going to be a little bit less, I guess, straightforward here because now we don't have a carbocation, but we will have sort of a semi carbocation intermediate, and I'll show you that when we get to it. So for the halohydrin formation, we're going to use both X2, in this case Br2, and an H2O. But the H2O will come in later. I'm just going to write it out to the side for now. So the first step, halohydrin formation, we attack with our nucleophilic double bond. Bromine attacks right back, and the bromine-bromine bond breaks. And so then we make our beautiful, our wonderful, our amazing bridged polonium ion intermediate with our positive charge here. And so this is where the oxygen, the H2O, comes into attack. And so now let's pause for a second because we know what's going to happen. The OH is going to attack one here. This bond is going to break. Let's talk a little bit about the transition state here. So if we draw the transition state of this reaction here, we can see that this bond with Br still exists. The Br is still partially connected to this carbon, which is partially connected to this oxygen here, this OH2. Okay? So all of these guys here, they're basically going to be having a partial positive charge because the bromine's bond is breaking, the carbon's bond is breaking, and the OH bond is being formed. So all of these have a partial positive charge. And the idea of a partial positive charge is the same thing as a regular carbocation. The more substituted it is, the better off, the more stable it is. So what that means, so the partial positive charge is on the oxygen, yes, sorry. And so what that means is we're going to want to put that partial charge on the most substituted carbon. So what that means is we're going to end up adding our OH, our OH2, to the more substituted carbons. Like for example, if this had something right here, and right here. Okay? So we're technically following Markovnikov, but we're sort of treating our halogen as the hydrogen. Okay? Because the halogen will go on the less substituted carbon, and then we will deprotonate with our Br. We'll grab the hydrogen, bond breaks, and we end up with our final alcohol product, or halohydrin product. Sorry. Oh, this whole thing here. This is called a halohydrin. That's why we call it halohydrin formation. Amazing, I know. Breathtaking. All right, so does that make sense why we sort of follow a pseudo semi Markovnikov with halohydrin formation, where we're treating the halogen as a quote unquote hydrogen? All right. All right, perfect. So that's halohydrin formation. That probably is the harder one of like the main four. So now we're going to get into sort of the derivatives of our hydration. So if there were equal substituents on each carbon, the placement does not matter exactly. So now we're going to get into sort of the derivatives of hydration using an acid. So hydration using an acid. So if you recall, hydration using an acid, we will end up adding Markovnikov and we will undergo rearrangement. So like for example, if we start with this guy here, we're going to make this carbocation, which will then do a hydride shift into this carbocation, and we will end up adding our OH right here. Okay? I just did that really, really quickly. I'll go over the full mechanism in a second. I just want to sort of go over each step of this because our next equations, our next reactions we're going to talk about are going to be sort of taking this hydration using an acid and sort of taking each step in a different way. Because what if instead of putting our carbocation right here, we wanted to add our hydrogen right here, and we wanted to add our OH here? We can't do that with hydration using an acid. In addition, this carbocation will always rearrange. But what if we don't want it to rearrange and we want to put our OH right here and our H right here? So I'll just draw out the three final products. So each one of these products can be obtained. This first one here, of course, we obtain it by just doing the regular hydration using an acid. This product here, this anti-Markovnikov product, because you can see here the OH added to the less substituted carbon, this is going to be a product of hydroboration oxidation. And this one here, where we avoid rearrangements, will be oxymercuration demercuration. Okay, so we can see here that hydroboration oxidation and oxymercuration demercuration, they're just basically derivatives of hydration using an acid, where we want different products depending on what we want in the end. Okay? Does this all make sense? So again, these next two that we're going to be talking about, derivatives of hydration using an acid, we're still adding H2O overall. We're just adding it in different ways. Okay? All right. So the first one I'm going to talk about because I'm overall more familiar with it, I guess. I mean, I'm familiar with both of them, but I've been teaching hydroboration oxidation for a long time because that's what a lot of people would come for me. So let's go with hydroboration oxidation first. So hydroboration oxidation. So if we break down this name once more, hydroboration, we're going to be adding hydrogens and a boron. Oxidation will be oxidizing something. And the definition of oxidation in organic chemistry is a little bit different from oxidation in Chem Chem. Oxidation in organic chemistry generally means that we're increasing the number of carbon oxygen or carbon halogen bonds. But again, we won't really have to worry about that too much until we get to oxidation reduction chapter. But I just want you to know our very slightly different definition of oxidation as far as organic chemistry goes. And again, I'll explain more why we describe it that way later, but I do not want to overwhelm you with information. All right. And we can also see that this is the first equation here that we've talked about that's really two words. So we had halohydration, hydrohalogenation, halogenation, hydration, all of those, halohydrin formation, all of those were basically one word. This one is two words, which means this is going to be two steps. The first step being the hydroboration, the second step being the oxidation. Okay? So the reagents that we're going to be using are generally going to be BH3 for the hydroboration. Usually this will occur in an aprotic solvent, and oops, I did not mean to do that. I meant to select the eraser. For the aprotic solvent that we usually use, that will be THF. You don't really need another structure, just know THF is an aprotic solvent. For the oxidation, we'll be using H2O2, which is basically just a peroxy acid, and then OH. This OH here is going to be what is going to be oxidizing. Okay? All right, so let's get into it. Let's get into this mechanism here. So just to be completely candid, generally the mechanism of hydroboration oxidation, you really only have to worry about this first step here, because this first step is what determines everything else. Okay? So this first step occurs, and we end up adding BH2 to the less substituted carbon and hydrogen to the more substituted carbon. And to investigate why this happens is we have to look at the transition state. I know you're probably tired of me saying that, but again, transition states are key. So of course, transition state, what's going to happen is the double bond will act as a nucleophile, The BH2 will also act as a nucleophile, and this bond will break, go on BH. Okay? So let's draw this actually happening in this transition state. So this double bond is in the process of breaking. This bond here with hydrogen is in the process of being formed. This double bond here, or sorry, not this double bond, but this bond with boron and hydrogen is in the process of being broken. And the boron carbon bond is in the process of being made. Oops, I drew them backwards. Sorry. I got too excited. But I put the boron and the hydrogen on the wrong side. And I did it again. I'm sorry, guys. Did I get enough sleep last night, I wonder? But we get there and there. Okay? So now let's take a pause and look at this. So what's happening? This bond here, this bond between hydrogen and carbon, it's being made and it's only really a partial bond. So this carbon here, we're going to give a partial positive charge. The carbon that has the partial bond with the hydrogen will have a partial positive charge. Whereas the boron, since it's losing a bond and it's gaining a lone pair, it's going to have a partial negative charge. Okay? This carbon here, it doesn't really care so much what's happening because it's not losing or gaining any bonds. Because if we look at this, we can see that this carbon with the partial positive charge, it's losing one of its bonds to create a new hydrogen bond. Whereas this one over here, it's not losing any bonds. It's actually creating a bond with the BH2. Okay? And it just dawned on me that I probably drew these a little bit misleading, but it's actually going to be more like this. But the other arrow is shorter, so I did that. All right, so does this transition state make sense to everybody so far? All right, and so the idea with this transition state is, again, we're going to want to put the partial positive. Can you explain the steps in which they attach again? So all of this is technically happening in one step, but I'm going to explain it like one bond at a time. Let me grab my highlighter. The nucleophilic double bond is going to attack this hydrogen. This double bond here is in the process of breaking. This bond here between the hydrogen and the boron, it has to break because, again, hydrogen can only hold on to 2 electrons. Boron wants a new bond. So what's going to happen? It's going to attack wherever that carbon, or whichever carbon does not gain the hydrogen, because again, we can't violate the octet rule. And so again, what's happening here? This carbon right here, the more substituted one, it's basically losing its double bond to create a new single bond. So it's in the process of losing a bond in order to make a bond. So we're going to consider it partially positive. This BH2, it's currently gaining a pair of electrons from the hydrogen, as well as giving a pair of electrons to another carbon. So it's going to be partially negative because it's gaining electrons overall. And so then we end up with this transition state. Does that help clear things up? And this transition state determines that the more substituted carbon is going to get the partial positive charge. So that means that the hydrogen is going to go to the more substituted carbon, okay? And so what this means is that the BH group will go to the less substituted carbon, okay? And so let's talk about, yes, so this is anti-Markovnikov. Let me write that down. This is anti Mark. It just hates that dude, Mark. Jeez. It's just anti-Markovnikov. And so let's talk about stereochemistry really quickly. And let me move the hydrogen right here so we can sort of compare it to the BH group. So the hydrogen and the BH, they used to have a bond together. So if we think about it really quickly, in this transition state, that bond is being broken. They cannot be on opposite sides if that bond is being broken. It's sort of like the bridge idea again. We can't have a bridge with 2 different sides. So that means that the BH and the hydrogen, those will be added syn. Okay? Does that make sense? Does everybody with me there? Okay, awesome. So the next step that occurs is we're going to have our H2O2 and our OH replace. Can they also both be dashes? Yes. Just as long as they're on the same type of wedge, whether it be solid or dashed, they're syn. Okay? And do you have to understand the mechanism or memorize the hydroboration or anti-Markovnikov? Memorizing the mechanism will help you further down the line, but if you need to for this test, you can just memorize its anti-Markovnikov. But again, I highly recommend knowing this mechanism and understanding what's actually happening. But I also understand that you guys have a test in 3 or 2 days, and that's a lot to memorize in 3 or 2 days, 2 or 3 days. Okay? And so this next step, it definitely has a mechanism, definitely, but we don't really go over it in this class just because it takes a lot of stuff from Orgo 2. So a lot of the times what you're just going to see is you're going to say, okay, the mechanism happens here. We don't have to know it, so we don't care about it. And what occurs is the OH is going to replace the BH on the same exact type of wedge. Okay? So we can see here that hydroboration oxidation, it adds anti-Markovnikov, anti-Mark, and it only adds syn. Okay? So remember, just to recap, whenever we have a carbocation, we'll be adding syn and anti. Whenever we add, whenever we have a halonium ion intermediate, we'll be adding anti. When we're doing this, we'll be adding syn. Okay, yes, that's a lot to remember, but I believe in you because it's very helpful to break it down, and I hope I broke it down enough to remember syn versus anti, anti versus syn sort of thing. Okay, all right. So let yes, I'm going to show you the chart. Don't worry, I'll share the chart. All right, so let's clear this. So we talked about hydroboration oxidation. Now let's talk about oxymercuration demercuration. And that's a lot of words. But essentially what's going to happen is we're first going to add an oxygen, and a mercury group. So O and Hg. And then we're going to remove the mercury group. So oxymercuration, we add an oxygen, we add a mercury. Demercuration, we get rid of the mercury. Okay? Does this make sense so far? Okay, awesome. All right, so let's go through that carbocation that we talked about before. So let's say that we have this guy here. If we were to do oxymercuration demercuration, what we're going to be using, we're going to be using a mercuric cation, which essentially looks like Hg plus connected to, honestly, we don't really care that much, but it's connected to oxygen with an acetate group on it. What's important in the product, it will be OH, but I'm just sort of explaining to you like the oxygen part is what we see in the name, but it will be OH. So we start with a mercury cation. What's important about this is the mercury cation. The OAC is less important. Okay? But the first step of oxymercuration demercuration is we're going to see what happens here. The nucleophilic double bond is going to attack that mercury group. Okay? And so then we end up with this guy right here. Hg, positive charge here, and then OAC. And so what's important to note here is that Hg is going to be partially negative. Since Hg is partially negative, it's going to attract that positive charge in a very similar fashion to our bridged halonium ion intermediate. So we're going to make a bridged mercuric ion intermediate plus ACO. Okay? So what we can see here is now we have a possible, we have this guy right here. We have this intermediate. And so what's going to occur is our nucleophile, aka water, I'll put an H2O here. Oops, that did not mean to write that. That H2O is going to attack the more substituted side of this sort of complex. Why? Because it's going to spend more time with the positive charge because of this sort of resonance structure here. Okay? Does that make sense to everybody? Okay. And so then what happens is we add our OH to this. And again, we went through deprotonation stuff, but what's important is we end up with an OH on the more substituted carbon, and we end up with HgOAC. Does the bridge form in one step like last time? It's more considered a resonant structure than before. Whereas when we did the bridged halonium ion intermediate, it would always only form the halonium ion intermediate. Whereas this one, it can exist in either state. But it's this guy here that prevents rearrangement. Okay? Does that make sense? And then what happens in step 2, we're going to be using something called NaBH4. All you have to know is it gets rid of the mercury and essentially just replaces it with a hydrogen. Again, we'll talk more about this specific reagent here, NaBH4, when we get into reduction and oxidation, because it is a reductant. But for right now, all you have to know is it gets rid of the mercury along and then replaces it with a hydrogen. And you don't really need to worry too much about the mechanism, because the mechanism is a little bit too advanced, I guess, for Orgo 1. All right, does this all make sense to everybody? And okay, so the reason why we use oxymercuration demercuration over hydration using an acid is because we avoid rearrangement. That's the big thing to take away from this reaction. Oxymercuration demercuration does not do carbocation rearrangement. Yes, rearrangements only happen with carbocations, as far as you know, but that's an Orgo 2 thing. Okay? All right, so that was all of the alkene reactions. Let me go over the list one more time. Hydrohalogenation, hydration, halogenation, halohydrin, oh, we have to go over dihydroxylation. But we went over the main I don't know, the big 5 or 6, I think. So let's write all of those down just really, really quickly. Is there any stereochemistry involved with this one? So, he does not have it written down in his PowerPoint, so I wouldn't worry about it too much. He has everything else written down about the stereochemistry except for this one. Epoxidation and oxidative cleavage. Yes, we will know about that one, but what I'm going on right now is we're knowing most of the addition reactions. Epoxidation, dihydroxylation, and cleavage, they're a little bit different than these ones that we've gone over. They're like in a different sort of field. So I kind of just want to go over these first. Isn't the bridge step kind of extra? Well, yes, the bridge step is extra, but we have to know that it exists because this bridge step is what prevents the formation or prevents the rearrangement of our carbocation. How would the reaction arrow be written with NaBH4? I don't know if I want to tell you because NaBH4 becomes this, then it attacks here, and it creates another one of those weird transition states, and then you replace it with a hydrogen, and it's just a lot that's going on. Because essentially what happens is the BH, or one of the B attaches to the mercury, the hydrogen attaches to this carbon here. This bottom, yes, I'm going to list out all of the ones that we've already done so far before we get into epoxidation, dihydroxylation, and all of that stuff. Okay, so let's clear this. Yeah, let's skip that. That was a lot. All right, so 1, hydro Halogenation. So hydrohalogenation, we start with our, oops, let me draw that a little bit smaller so I can fit everything on here. We start with our double bond here. We use HX, where HX is HBr, HCl, HI, and we end up with syn and anti products. So I'm going to put X and put something right here, H plus X, this guy here, H. So syn and anti, and it's Markovnikov. 2. Hydration using an acid. We have our guy right here. We're going to use an acid. I'm just going to put H3O here plus, and water. We end up adding syn and anti and Markovnikov, just again. Sorry, meant to write an H there, but I started writing an O. OH, methyl group right here, and hydrogen right here. So we have syn and anti, and this is Markovnikov. 3, I'll write up here, 3 is going to be halogenation. All right, halogenation, essentially we end up with, we're going to use X2, which X is IBrCl once more. We're going to add only anti because of the bridged halodyl ion intermediate, so anti only. Sorry, I can only write so fast. And this, we don't worry about Markovnikov because we can't differentiate between the two halogens. They're basically the same thing. Right? 4, Halohydrin. We're going to use X2 along with H2O. So in this case, what you'll usually say is either 1 X2 and 2 H2O, or you can also write it as X2 over H2O, because H2O can also act as our solvent. And so then we also end up with anti-addition only. Oops, meant to draw that as a dashed wedge, whatever. And we can see here that we add in a pseudo-Markovnikov way, wherein the X, our halogen, adds to the less substituted carbon. So anti, and then plus, I'm going to put like about Markovnikov. It's something very similar, okay? So now I'm going to say 2A. I'm going to come back to 2, and we're going to say hydroboration, put capital B, hydroboration oxidation. And we're going to say we have this guy right here. We're going to use 1BH3 in a nonpolar solvent, or a protic solvent, THF, and then 2H2O2 OH negative, and we end up with only the syn product. So we end up with, let me write that, H here, OH here. So this is syn only. We could also have it as the dashed wedges, OH, OH, this guy here, syn. And this is anti-Mark. He hates Mark. Okay? And then 2C, this is going, oh, I'm sorry, 2B. I skipped B. Will 4 have anti only? Yes, only anti. 9BBN also works for hydroboration. So 9BBN is basically a derivative of BH4, where you have 2 R groups. So like it looks kind of like this. We have like Carbo. That should be a B right there. We have something that looks like this. Yes, 9BBN works for hydroboration. But the big thing is you have that boron somewhere. Okay? 2B, oxymercuration. What is the purpose of having THF and H2O2? THF is an aprotic solvent that allows the BH3 or BH4 to react, whereas the H2O2, that's kind of what causes the oxidation. They're both pretty important. The one that's probably less important would be THF. So oxymercuration demercuration. We are going to I guess I should have made this, I'll make this look like this. So we know that we avoid rearrangement. And as far as I know, you don't really need to know Syn and Nancy as far as oxymercuration demercuration goes. So we're just going to leave that out. It adds Markovnikov, and it avoids carbocation rearrangement. Oop. Running out of room. Okay, so these are all the ones that we've gone over. Oh yeah, it should be H, sorry. Meant to write H right here. Okay, so these are all the ones that we have gone over so far. Feel free to take a screenshot or whatever. Does anybody have any questions about this? Yeah. I'm gonna take a sip of my water really quickly. All right. So if nobody has any questions about this, I'm going to, does oxymercuration, alkoxymercuration. That's what this is, basically. So the idea of alkoxymercuration is you don't have OH, you have basically OR, where R is another like another alkyl group. That's what alkoxy means. It means you have an alkyl group attached to an oxygen. Okay? What's handwritten next to the plus side for halohydrin? It's like semi Markovnikov. So I just put like an almost Markovnikov mark. Later on, will we get an example of an oxymercuration with a chiral center? We'll talk a little bit about that later at the end because I kind of want to go through everything, and we're not super far through this chapter yet, but we have gone through a lot. Okay? All right. All right, so now we're going to get into the epoxide formation, which will be closely followed by the dihydroxylation. So the epoxidation is going to basically take this double bond and turn it into something called an epoxide. So this is very similar to our bridged halonium ion intermediate, but this is non-ion because remember oxygen likes to have two bonds and it's neutral when it has two bonds, okay? The way that we get this dihydroxylation is through something called a peroxy acid. So it's going to be, so it's generally going to have the structure of this. Okay. I may have called H2O2 peroxy acid. That would have been a misspeak on my part. I meant something different, but I digress. So this is a peroxy acid. And the main peroxy acid that we'll use in this class is called meta-chloro peroxy benzoic acid. Just know MCPBA is going to do epoxidation. Okay? The reason we use MCPBA is because it's really, really stable and it's easy for us to use. All right? All right, so the mechanism for this occurring is essentially going to be, so we have our peroxy acid right here, and we have our oxygen right here. So essentially what happens is the same thing that happens in the formation of the bridged halonium ion intermediate. The double bond reaches up, grabs the oxygen. The oxygen reaches back down to grab the carbon. Great, but now we have to break some bonds. This OH bond here is going to break and go on to this oxygen here, or we can just write it as this bond is going to steal this hydrogen, and then this bond is going to go back on that oxygen. So we can see here that all that's happening is we're sort of removing this oxygen right here to create our epoxide. And we can see, if I can draw, we create our epoxide right here. And again, it's going to be on the same type of wedge because a bridge is a lot more stable if both legs are on the same side. Okay? Okay, so does this all make sense to everybody? Okay, awesome. All right. And so similar, so I'm going to erase this very quickly. So now we have an epoxide. There are a couple things that we can do with epoxides, but the main thing for us right now is something called dihydroxylation. Essentially, we're going to be adding another oxygen, another OH group to this guy right here. So what we do is we have H2O or OH negative or H plus. It doesn't really matter, but in this case, we're going to use H2O. And again, just like when we did halogenation, this bond is going to break at the same time as the hydrogen or the oxygen will attack, and we end up with this guy right here. And you may be able to guess, but it will be adding anti because again, we're going to proceed through a backside attack because of that bridged selenium ion intermediate. So we have these guys right here, and there are a few more steps, but essentially what's going to happen is this oxygen right here is going to steal a hydrogen from the OH2 over here, and we end up with our final dihydroxylation. Okay? And this is going to be anti-dihydroxylation. To do anti-dihydroxylation, you have a double bond. You treat it with something called a peroxy acid, which is essentially RCO3H, mostly MCPBA. Then we treat it with water, which then forms our anti-dihydroxy group. Okay? Does that make sense? Okay, awesome. So this is anti-dihydroxylation, but what if we want to do syndihydroxylation, which means we add the dihydroxy to the same side? Well, what we would do there is we wouldn't even use an epoxide. Which part of this process is the dihydroxylation? The dihydroxylation is sort of this whole process here is dihydroxylation because the end point is going to be the dihydroxy group. It's just this portion at the start is also called epoxidation. Okay? Because we have to have an epoxide to do the anti-dihydroxylation. All right. So to do syndihydroxylation, we're going to do something a little bit different. We're going to have our double bond right here, and we're going to use either KMNO4 or OSO4. The big giveaway is if you see O4, you're probably going to be doing syndihydroxylation. All right. And so what occurs is we're going to use KMNO4 or OSO. They look essentially the same when we look at the Lewis structure. It's just that KMNO4 has Mn and OSO4 has OS. So we have this and then we have this here. Okay? And essentially what is going to happen is this double bond is going to grab here. This bond will break. An oxygen is going to grab over here. This bond will break. So this is similar. This is very similar to the epoxidation, where an oxygen is going to be attached to either side of the double bond. It's just here these are two separate oxygens rather than being two of the same oxygens. Sorry, did not mean to draw a double bond there. We end up with oxygen here, Mn, oxygen here, Mn, oxygen, oxygen. And then essentially we're going to treat this with H2O, which will break everything apart, don't need another mechanism, and we end up with two hydroxy groups on the same side. And the reason why they're on the same side is because these bonds here, these bonds, the Mn, are sort of holding them in place, preventing them from moving to a different type of wedge. Okay? So this is the syndihydroxylation. We can also do something called catalytic syndihydroxylation, where instead of using KMNO4 or OSO4, we're going to use OS8 plus. But again, this is not a mechanism you really need to know for this class. But just know that Syndihydroxylation can be done with KMNO4, OSO4, or OS8+. Okay? That's Syndihydroxylation and Anti-Dihydroxylation. Easy. Easy stuff. Easy money. All right? How does everybody feel about that? Easy points, exactly. And the big giveaway for the Syndihydroxylation is the KMNO4 or OSO4. You may see other reagents like Na2SO3 and water, but that's just basically to keep this OSO4 or the KMNO4 sort of controlled so it doesn't react out of hand. Dihydroxylation, only anti-dihydroxylation occurs with epoxidation. Syndihydroxylation occurs with something that's similar to dihydroxylation, but it's not. It's different, okay? Does that make sense? Where and when, this will go on my YouTube after the recording. It takes a little while for it to render, but I expect it to be on YouTube by tonight. The reagents to use for anti-dihydroxylation, so let me clear my screen. So anti is going to use RCO3H, which is a peroxy acid, usually going to be MCPBA, followed by water. Syndihydroxylation will use KMNO4, OSO4, followed by a number of reagents, but what's most important is going to be the water, H2O, or we can just use OS8 plus. Okay? Does this make sense? Okay, awesome. All right, and so now we're going to talk about probably the easiest part of this chapter, ozonolysis and metal catalyzed hydrogenation. Okay? So the idea of metal catalyzed hydrogenation is we take our alkene, we combine it with hydrogen on a metal, so like palladium, caladium, whatever. And then what happens is the hydrogens are just added to the same exact side. So this is synhydrogenation. And the reason why it's synhydrogenation is essentially, basically, if we think about it, this is called hydrogenation. When we use the metal, what's going to happen is the double bond is going to kind of stick to that metal. And then the hydrogens are going to come in and they're going to attach from either side of that metal here and here. Okay? Does that make sense? All right. Okay, awesome. So that's why we do synhydrogenation. Again, hydrogenation is just called that because we're adding a bunch of hydrogens. All right? And so now, my favorite part, we're going to be doing ozonolysis. So ozonolysis is really, really easy because all you have to do is just say, okay, I have an ozone. The main part of this reaction is the ozone. You can see ozone with zinc, ozone with HCl, ozone with other things, but what's important here is the O3. And what you're going to do when you see O3 is you're going to take this double bond and you're going to draw a line straight through the middle. Then you're going to redraw that double bond with sort of a gap between them where that line sort of was. And in that gap, you're going to cap it with oxygens. So our final products are going to be this guy here plus this guy here. And the reason why I've drawn it like this instead of like this is because this is what you're usually going to see in like a multiple choice question. All right? But you can see here, ozonolysis, super easy. All you do is you replace the double bond, you cut it in half, and you sort of cap it with oxygens. Okay? Ozonolysis, super easy, really awesome for you guys to it's a really awesome question to see on a test because it's not super hard. Okay? Does that make sense? All right. One thing that I think I want to go over just really, really quickly is the difference between anti-products when we have something that looks like this versus something that looks like this. So an anti-product for this guy is going to look like this or this after we've twisted things around. Okay? If we have an anti-product with the bottom one, it's going to look like this or this. Okay, so we can see here that depending on the configuration of our alkene, that will sort of change what our anti and our syn products are going to look like. So you can see here that this product right here, this is a meso product because of this line of symmetry right here. So we have to be sort of careful with that because I don't think I covered it as well as I wanted to when I talked about it when we did halogenation. But if you look here, the anti-addition can produce meso compounds. It's just in specific areas. Okay, and I think that's the end of chapter 8. Yeah, I think we've done everything. Does anybody have any questions about that? Yes, both of these answers, like these two answers that I've drawn, they're both anti-answers for the sort of stereoisomer that I had of the double bond here. Yes. Well, basically what's happening here is when we turn these wedges around, when we sort of flip these guys around, they become both solid wedges. Okay? Okay. So let's do this. So epoxidation, so I'll put epox here, uses just RCO3H, peroxy acid, mostly MCPBA. What happens here is we have a double bond and it turns into an epoxide. Syn, or sorry, let's do anti over here. Anti-dihydrox will use epoxidation, so RCO3H plus an H2O. And what's going to happen here is we're going to have our guy right here, and we end up with OH groups on opposite sides because we have an epoxide sort of intermediate. Syn dihydroxylation is going to include KMNO4 or OSO4 plus water, or OS6 plus, and I'm sorry, not 6 plus, but 8 plus, misspoke there, 8 plus, and we go from this guy to this guy. And again, we could form the other versions of these, but I'm kind of going through it fast because we still have a whole chapter to cover. And then the last one is, the second to last one is going to be a zonolysis. I'm going to put ozone here. As long as you see ozone, we're going to undergo a zonolysis. And essentially what happens is we cut the double bond in half and cap it with oxygens. Okay? Finally, hydrogenation. Basically, we're going to be using H2 with a metal catalyst, usually palladium. And we end up with just hydrogens added to the same side in the same way. All right, so this is the summary of what we went over after we went over sort of the general addition reactions, okay? Anybody have any questions about this? All right, then I think we're about ready to move on to chapter 9. All right, so I'm going to go over one more thing with chapter 8, and then I think we're good to go on to chapter 9. All right, so I'm just going to go over just the anti idea one more time. So depending on the stereochemistry of our alkene, our syn and anti products can look different because alkenes are sort of stuck in this position. They cannot freely rotate. So we're either going to have this alkene or this alkene. They do not rotate freely. So when we add anti, we have to think about that because if we add anti to this first one up here, it's going to look something like this. If we add anti to this guy down here, it's going to look something like this, where we can see that the stereochemistry stayed the same and the bromines were added anti. But when we rotate these to look a little bit different so they look like each other, when we rotate around this bond, we end up getting something that looks like this. something that looks like it shouldn't be anti. And if we rotate this around, we get a a meso compound, because we get this line of symmetry. So because of the stereochemistry of the alkenes, that will determine our sort of stereochemistry of our final product. Okay? Does that clear things up with this here? Okay. Okay, awesome. So now we're going to go on to chapter 9. Yay! And again, like last time, I don't think I'm going to go over nomenclature that much, because that's easier to look up online than all of this stuff. And we've been going for about 2 hours now. The YouTube video might be a little bit shorter because we did pause for a few breaks. But talking for 2 hours is a lot, and we're going to go strong for another hour. Woohoo! Anyways. So alkynes, just like alkenes, we can create them. We create them from something called a dihalide. There are two different types of dihalides, a geminal dihalide and a vicinal dihalide. And I'll tell you why they're named that in a second. So a geminal dihalide would look like this. So I'll put gem down here. And a vicinal, VIC, is going to look like this. So we call them a geminal dihalide because if you think about the root word of geminal is Gemini. That means twins for all the guys that aren't into astrology, all the guys and gals and others that are not into astrology. But geminal dihalide, Gemini, they're twins, so they'll be on the same carbon. A vicinal dihalide means they're in the same vicinity, so they're on adjacent carbons. This is not a vicinal dihalide because they aren't on adjacent carbons. They aren't on the same vicinity, so we do not call this a vicinal dihalide. But anyways, I digress. Whenever we have these guys here, a dihalide, we can undergo elimination twice. And when we undergo elimination once, we form one double bond. When we undergo elimination again, we form another pi bond, and as a result, we create our alkyne. Again, a reminder, alkynes are anything with a carbon-carbon triple bond, and the reason we draw it like this is because the carbons on the either side of the triple bond, they are linear. So we want to reflect that in our drawing, okay? All right. So that's how we generally make a dihalide, or not a dihalide, but a triple bond here. And one thing that you should sort of be thinking about right now is, well, how do I make these dihalides? Well, we know how to make the vicinal dihalide. We know how to make the vicinal dihalide because that is just halogenation. We did Br2, halogenation, and we end up with this. That creates our vicinal dihalide. So if we want to go from an alkene to an alkyne, we would have to halogenate that alkyne first and then undergo elimination twice. Okay? Does that make sense? And this will feed into synthesis. So spoiler alert, synthesis is just combining all the different reactions that you know together in order to get a certain product. And so, for example, if I said, synthesize me an alkyne from an alkene, our synthesis would consist of, oh, well, to make an alkyne, I need to have a dihalide. To make a dihalide from a double bond, I just have to do halogenation. And then I eliminate once to make a new double bond here. And then I eliminate again to form our alkyne. This is synthesis. This is again just sort of like a rudimentary version of synthesis, but it's the same idea. We have our reactant, we have our product. We know that we want to go from our reactant to our product, so we think about all of the reactions that we know of to get to that product. So a little sneak peek to synthesis, but we'll talk more about that later. Okay? But that's how we make an alkyne. All right. So the next thing that we should probably talk about are the reactions of alkynes. And we had like a billion different reactions for alkenes, and we are going to have a few reactions for alkynes as well. But the reactions for alkynes are going to be very, very similar to the reactions of alkenes. Let's take halohydration, for example. So again, I'm sorry, I keep saying it backward. Hydrohalogenation. So again, when we do hydrohalogenation, we're going to be using HX. But the idea here is we have two pi bonds. We have two pi bonds that can act as nucleophiles that can interact. So we're going to use two HXs. And the way that this is going to work is going to be the same thing as with alkenes. Step one, we form a carbocation. Woo! And again, we're going to form the more substituted carbocation. But in this case, it didn't really matter because both carbons are equally substituted. The only time that one carbon will be more substituted than another is if we have a terminal alkyne. That means that one of the carbon bonds is taken up by a hydrogen. Okay? All right. So then we make this positively charged carbocation. Then we add our bromine, and now we are here. And then what happens? We just do another hydrohalogenation, just like we saw before when we were doing our alkene reaction. Again, we'll form a carbocation, and surprise, surprise, the hydrogens end up on the same carbon, and then the bromine attacks again, and the bromines end up on the same carbon. Okay? And so we can see here, this is a geminal dihalide. So now we know how to make both a vicinal or geminal dihalides. It's just a lot of the times to make an alkyne, it's more beneficial to make a vicinal dihalide. Why? Well, we need an alkyne to make a geminal dihalide. So if we're trying to make an alkyne, but we need an alkyne to make a geminal dihalide, we're just running around in circles. So a lot of the times you're going to see vicinal dihalides used more to create an alkyne rather than those geminal dihalides. Okay? Does that make sense? All right. And one thing to note here is that this can either be E or Z, which means we can either have the high priorities on the same side or the high priorities on opposite sides. Why can it be E or Z? Well, again, let's look at the intermediate here. The carbocation intermediate means that our halogen can add to either side. Now, we don't really have dash wedges or solid wedges as far as alkenes go, but we do have E or Z, which is where this comes in. Yes, you should know the mechanisms, but what's lucky about this is the mechanisms are all very, very similar to what we've done before with the alkenes, where we can see here, first a hydrogen is grabbed by the pi bond, and then we make the carbocation, which then is grabbed by the bromine, and so on and so forth. Okay? Does that make sense? And also something to note is we need 2 copies of our HX to finish this off because we have 2 pi bonds we have to add to. All right? Okay, awesome. Okay, so now let's talk about halogenation as far as triple bonds go. So halogenation, essentially what's going to happen is we're going to add 2 sets of X2 to this guy. So we're going to end up looking like this. And we're gonna call this a Tetra Halide. Tetra means 4, halide means halogens. We have 4 halogens on one of our carbon chains, so we call this a Tetra Halide. And the way this works is again through halonium ion intermediates. So again, we're gonna use Br. I really like using Br. The Br will attack one of the carbons at the same time as a pi bond attacks the bromine. This bond breaks, and again, we're going to make a bridged halonium intermediate. But what's important to note here is that we don't have any stereochemistry because we only use solid wedges or dash wedges when we are talking about sp3 carbons. Both these carbons here are sp2, so we don't use solid dashes or wedges. I'm sorry, wedges or dashes. All right. And the same thing happens as did before. The bromine grabs onto one of these carbons, this bond breaks, and we end up with, drumroll please, a trans product. So that's something to note here. So before we could end up with either E or Z, but when we're talking about halogenation, we can only end up with this trans product. And this is because, again, because we have the bridged halonium ion intermediate, and the BRs are going to want to add opposite to each other, okay? And so then, same as the first, we have our two bromines. One of them is grabbed by the double bond, and it grabs the double bond right back. This bond breaks, and we end up again with a bridged halonium ion intermediate. This time, though, we do have stereochemistry if the answer has it drawn in. If not, then don't worry about it. And then we have this here and this here. Okay? And then, oops, wrong color. And then our negative BR, again, is going to attack this one right here. And we finally end up with our Tetra Halide. Okay? And what's important to note here is that we aren't super concerned about stereochemistry. Why? Because we do not have any chiral centers here, because we added the same thing twice. See here, this isn't a chiral center, this is not a chiral center. So we do not worry so much about stereochemistry when it comes to alkyne additions, because we do not end up with chiral centers usually. Okay? So that was hydrohalogenation and halogenation as far as the actual triple bond, the alkynes go. So those, just like the alkene reactions, we just add them twice. Okay? Sorry. So now let's talk about acid catalyzed hydration and hydroboration oxidation. We do not generally do oxymercuration demercuration with alkynes. We only really do that with alkenes. So now let's look at the alkynes and let's look at hydroboration oxidation versus hydration using an acid. So if you recall, the main difference between hydroboration and hydration using an acid is hydroboration oxidation is an anti-Markovnikov reaction. Well, if we have an internal alkyne, those that are flanked by carbon bonds, then it won't really matter much because adding to either carbon will basically be equivalent. Okay? So if we have an internal alkyne, we're going to end up with the same type of product no matter if we're doing hydroboration oxidation or hydration using an acid. I'm going to skip the mechanism for hydroboration oxidation because remember, you end up, actually, I'll just draw it out because I know you would love it if I did that. So we end up with BH2 here, H here. So this is going to be BH3. And then we're going to oxidize with H2O2 and OH. And we end up with this guy right here. And the same thing is going to happen here, except first the hydrogen will attack. We end up with a carbocation. Let me put the carbocation over here so we're adding to the same side. We have H2O, which then is added to the carbocation, and then we deprotonate, and then we end up with the same exact alcohol here. Okay? And these are special alcohols. We call these enols. Why? Because we have an alkene next to an alcohol. So we combine those names together and we call it an enol. Okay? Does that make sense so far? All right, awesome. So the funny thing about enols is that they have a very particular constitutional isomer. So let me draw that constitutional isomer for you. So I'll just draw this. We have this right here. And this right here. So we can see here in these constitutional isomers, the pi bond and the hydrogen were the only things that moved. When you only move a pi bond or a hydrogen, and a hydrogen, we're going to call this tautomerization. And each one of these constitutional isomers, they're called tautomers of each other. They're special constitutional isomers that were formed by the movement of only a pi bond and a hydrogen bond, so we call that tautomerization. And overall, this product here with the carbon double bonded to the oxygen is more stable than the enol product because the oxygen prefers to have that electron density around it, whereas carbon does not. So overall, this form here with the double bonded carbon to oxygen will be more stable. Okay? Does that make sense? Okay. Awesome, 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 awesome. So, what's the name of the top one again? Uh, both of these are so the top reaction here, this one here. This is acid catalyzed hydration. This one down here, this is hydroboration oxidation. And these are called ketones. Yes, exactly. So you can see here that when we do either hydration using an acid or hydroboration oxidation with an internal alkyne, we are going to end up with a ketone. Okay? Does that make sense to everybody? Can I clear my screen? Right. And one last thing to note, when we're doing hydration using acid as alkynes go, we'll be using H2O, H2SO4 like before, but we'll also be using HgSO4, which just overall stabilizes the reaction, sort of like oxymercuration demercuration. Okay? All right. So now we're going to talk about terminal alkynes as far as hydration using an acid versus hydroboration oxidation. So if we do hydration using an acid, of course, we're going to add our hydrogen to the the less substituted carbon, thus putting the positive charge on the more substituted. Then we add the OH, and we end up with this guy right here, which then tautomerizes into a ketone. Okay? So with terminal alkynes, hydration using an acid will turn out making a ketone. Now, on the other hand, if we do hydroboration oxidation, we will end up with something a little different because we're going to have BH2 over here and hydrogen over here. Then we replace that with an OH, and then we tautomerize, and now we make something called an aldehyde. The way that I remember aldehyde is aldehyde has an H in the name, and the aldehyde here has an H at the end of it, okay? So we can see here with terminal alkynes, whenever we do acid catalyzed hydration, we will still end up with ketones after tautomerization. However, with hydroboration oxidation, we're going to get an aldehyde after tautomerization. That's the big difference here. Okay? Does that make sense for everybody? All right. Awesome. So we've gone over hydrohalogenation, hydration, halogenation for all of these different for alkynes. All right. So now what we're going to talk about is reduction of alkynes. Sorry. Yes. Internal alkynes will produce ketones because of the impossibility of doing Markovnikov addition. Whether or not you're doing hydroboration oxidation or hydration using an acid on a terminal alkyne, you will end up with a ketone. I mean, internal alkynes. Sorry. Internal alkynes always end with ketones. Terminal alkynes will end up with an aldehyde if we're doing hydroboration oxidation, or or a ketone if we're doing hydration using it with an acid. Enols, they do not show up very often as a product just because ketones and aldehydes are far more stable. However, if a question is specifically asking for the enol, then you'll pick the enol. Okay? We use enols in organic chemistry too for different types of reactions. You don't need to know that now. Okay? Does that make sense? Okay, awesome. Awesome, awesome, awesome. So now we're going to talk about reduction. Again, organic chemistry has a slightly different definition of oxidation and reduction, where our definition of reduction is if the number of carbon hydrogen bonds goes up, then we have reduced. And so if we look back, if we compare alkanes to alkynes to alkenes, we can see that alkanes will have the maximum amount of hydrogens. They're fully reduced. Alkenes will have 2 less hydrogens. They're slightly less reduced. And finally, alkynes will have the least amount of hydrogens. Okay? So when we reduce, we're either going to go back to an alkene or all the way to an alkane. Okay? You'll notice that we did reduction with our alkene when we did hydrogenation using a metal. And we can do that same thing here. The issue is when we do hydrogenation using a metal with a alkyne, we're gonna reduce all the way into an alkane. And while this is beneficial sometimes we do just want to reduce once into the alkene. So we have some special reagents for that. So if we want to reduce into an alkene, if we want to reduce to the cis alkene, we're going to use H2 along with something called Lindlar's catalyst. And I have a lot of questions about, do we have to memorize Lindlar's catalyst? Do we have to memorize the structure of Lindlar's catalyst? You have to recognize the name, but I wouldn't say you particularly have to memorize the structure. So just know that Lindlar's catalyst, along with H2, will form cis alkenes. Okay? On the other hand, if we have sodium along with liquid ammonium, we will end up creating the trans alkene. We'll reduce once into the trans alkene. Okay? Does that make sense so far? All right. So the cis alkenes, the Lindlar's catalyst, we don't really need to know that mechanism very well, but we do sort of need to know the mechanism of this reaction here. And this reaction is called the dissolving metal reduction. The reason we call it dissolving metal reduction is because we're dissolving sodium in liquid ammonium, and we're using that to reduce an alkyne. If the order of H2 and Lindlar's catalyst was reversed on the arrow, would it matter? Like up here? Like if it looked like this, I don't think it would matter, but it technically would be incorrect to write it out. So always write it out this way, but like if you have an answer that's only this and it doesn't give you this, I would say like choose that one as the answer. But it's not technically wrong, but I would not write it out that way because again, that's more points that you could potentially be losing. And you don't want to lose points, especially not in a test. All right, so let's erase this. Actually, let's clear everything. And we'll go through the dissolving metal reduction reaction. Now, this reaction, this is what's known as a radical reaction. This is what you're going to be going over next week. Well, after the test, next test. But essentially what's going to happen is in the ammonium, the sodium is sort of going to dissolve into a radical. And a radical is something that lacks an electron pair, but it does have this single electron here. Okay? And so essentially what's going to happen is the sodium is going to donate its lone electron to one of the carbons of the triple bond, which forces the pi bond to break homolytically, which means one carbon will get one electron and the other carbon will get the other electron. And so then we end up with this guy right here, where we have the full negative charge here and the sort of a lone radical right here. And now we know that opposite charges opposite charges repel. So they're going to want to stay as far apart from each other as possible. So that means that they're going to take up the trans configuration rather than the cis configuration. Because if I were to draw out the full like electron clouds here, you can see here that if we draw them in the trans configuration, that makes them farther apart than the cis configuration. So that's why we prefer the trans configuration when doing the dissolving metal. So then what happens is the NH3 liquid, the liquid ammonia, is going to basically donate one of its hydrogens to the carbon with the full lone pair, and then we're going to end up with this. And so then what happens is another sodium comes in, another sodium ion or radical comes in, it donates its other lone pair here, and we end up with a full pair of electrons on the other carbon here. And again, the ammonium group will donate another hydrogen, and then we will finally end up with our final trans product. Okay? Do we understand how this is happening? Again, you don't need to know the ins and outs of radical mechanisms as a whole, but you should know, or you should note, like, what is happening right here. The radical wants to stay as far away as possible from the double bond. And to do that, it'll take up the trans conformation. All right, does that all make sense to everybody? I don't know if you can hear my chair squeaking, but I have a squeaky chair. Okay, awesome. All right, so that is the reduction of alkynes. So now let's go on to ozonolysis. So this one is also quite easy, but it's a little bit harder than when compared to the ozonolysis of alkenes. So again, the main portion of ozonolysis is we have O3. And similar to the ozonolysis of alkenes, we're going to sort of slice this triple bond in half. But what's important to note is that oxygen does not like having 3 bonds. So instead of replacing that triple bond with one triple bond to oxygen, we're going to replace it with one double bond and one single bond. Okay? So in this way, we're still replacing that triple bond with an oxygen triple bond, but we sort of split it up into 2 separate oxygens. Okay? So the way that I always did this reaction, the way that I always did this is I would redraw again the triple bond connected to an oxygen. And then I would say, okay, what would this look like if instead of being connected to a triple bond, we have a single bond here and a double bond here. Same with this one. And then I would redraw this normally so it looks normal when I select the final product. Okay? Does that all make sense? And so we can see here that we form carboxylic acids. So when we cleave internal alkynes, we end up with carboxylic acids. When we cleave terminal alkynes, we're going to end up with 1 carboxylic acid and 1 mole of carbon dioxide, CO2. And the reason for this is because this structure that would form given like the same rules that we've been going over, this structure here, this is shockingly unstable. This will sort of decompose into CO2 and H2 gases, which is why we get CO2 when we cleave an not internal, but a terminal alkyne. Okay? Does that make sense? I say does that make sense a lot. You should start counting. That'd be start counting, and every time I say it, just tell me. Just count them up and tell me at the end in like the comments or something. All right, but you see here, internal alkynes create carboxylic acids, 2 of them. Terminal alkynes will create 1 carboxylic acid and 1 portion carbon dioxide gas. So if a question were like, oh, which one of these will give me exactly 1 product, what you're going to do is you're going to see, okay, which one of these is symmetrical? Well, this one isn't symmetrical because it has a hydrogen right here. So it's going to give me a carbon dioxide and CO2, which is 2 products. This one is symmetrical. This one will give me a single product from either side. This one will give me 2 different products because we have 2 different sides to the internal alkyne, which means that this one will give us a single product because it's symmetrical. So if you see a symmetrical alkyne, that will give you exactly 2 of the same products. Okay? All right. So that was ozonolysis. All right, so now we're going to get into the fun stuff, the meat and the potatoes. We're now going to be talking about acetylide ions, and this is really, really scary when you first see it. So when we talk about acetylide ions, these are derived from terminal alkynes. So we have this terminal alkyne and we form this guy right here. How do we do this? Well, what we do is we have a very, very strong base. We have it steal this hydrogen and this bond here will break. The bases that will do this are going to be NaH, because that forms a negatively charged hydrogen ion, NaNH2, not NH3, because this will dissociate into NH2 minus, and an organolithium. What we mean by organolithium is we have an alkyl chain connected to a lithium, because what this will do, this will dissociate into a negatively charged alkyl group, which then will attack that hydrogen as a very, very strong base. But these three are the main three that you'll see. These top two you'll tend to see more than the organolithium reagent, but I digress. So if you need a strong enough base to deprotonate a terminal alkyne, you're going to think NaH, NaNH2, RLI, that sort of thing, okay? And the reason why these are strong enough to deprotonate is, again, it has to do with acid-base rules. Remember, whenever we have a very high S component, sp, that's going to make that carbon, that hydrogen attached to that carbon, more acidic. And why can't we do it with internal alkynes? Well, we don't have a hydrogen to donate, so we can only make acetylide ions with terminal alkynes, with hydrogens on them, okay? All right. So what's the big deal with terminal alkynes? What's so cool about them? Well, if we look at this terminal alkyne is considered a very strong nucleophile. And with strong nucleophiles, we can do a bunch of different things, such as SN2 reactions. So what we can do here is we can do an SN2 reaction, replace that chlorine with this acetylide ion, and then we increase our carbon chain. So let me redraw this like this. And I'm going to give you a hot tip that is going to help you throughout the rest of chemistry. Number your carbons in your reactant and your product. So like, for example, so this will be 1, 2, 3, and this will be 4, 5. When I look at my product, I'm going to say, okay, so 1, 2, 3. There's a bond between 3 and 4, 4, 5. Uh-oh. Did I add a hydrogen or add a carbon here? So I bet none of you really caught that I wrote this product out wrong. And that is why we need, I'm sorry, the bond will be between 5 and 4. Sorry, I lied. 5 and 4, or 5 and 3, sorry. So you can see here that when you number your carbons, you're less likely to make a mistake. So you can see here that I made the mistake of extending this out one more carbon because I didn't number it. So always, always, always number your carbons. That is going to help you throughout the rest of organic chemistry. Okay? Does that blow your mind? All right. So another name that we have to think about here is, oh my gosh, this is the first time we've ever been able to make a new carbon-carbon bond. The reactions when we make a new carbon-carbon bond, this is called a coupling reaction. Okay? So if we're increasing the number of carbon-carbon bonds, we're doing a coupling reaction. We're coupling two different carbons together. Okay? Does that all make sense to you? All right. And so now, basically, all that's left for this chapter is organic synthesis. So I'm going to tell you that what you should do while you're practicing these organic synthesis problems is you should have a list of all of your possible equations that you can do. So like the hydrohalogenation, halogenation, hydroboration oxidation, you should have those written down. Eventually you'll have them all memorized like me, because you'll live and breathe organic chemistry. But for now, you should have them all written out, because what we could do is, I think this was similar. I don't think this is the same question that was on your on your on one of the worksheets that we did in class. I don't think this is the same one, but this is something similar. So now we see, okay, so we start with an alkyne and we end up with an aldehyde. And we're like, oh my God, how do I do this? I don't know how to do this. I quit. I'm dropping out. I'm withdrawing. What's the withdrawal date? But breaking it down is going to make it seem a lot easier. So the first thing that I always like to do when I was given these, October 30th is the withdrawal date, by the way. When given these questions, I would number my carbons of my reactant, and then I would number the carbons of my product. If I see that I end up with more carbons than I started with, I know that I had to do some sort of coupling reaction. So we know we did some sort of coupling reaction. So we extended the amount of carbons that we have. The only coupling reaction we know how to do is the acetylide ion. So I'm going to put acetylide reaction. Okay? All right. So the next thing we should look for is we should say, okay, so I go from an alkyne to an aldehyde. I went from an alkyne to an aldehyde. Well, I know how to do that. A terminal alkyne undergoes hydroboration oxidation, HBO. That's also a where you would watch Game of Thrones. HBO, that will give us an aldehyde. So the two big reactions here that we're going to have to think about is hydroboration oxidation and the coupling reaction. Okay? Does that make sense so far? Okay. So we know that both of these reactions happened at some point. Which one happened first? Let's think about this for a second. So there's something that we haven't touched on yet. That's called retrosynthetic analysis. And that's a whole lot of words for saying we're going backwards. And when I say going backwards, that means I'm going to look at this product here. I'm going to draw this arrow here and I'm going to say, okay, well, it looks like a smiley face. But I'm going to say what came directly before this aldehyde. So I know to form this aldehyde, I would have had to done hydroboration oxidation with a terminal alkyne, which means I underwent tautomerization. So the enol that I would have gotten this from would have looked like, would have looked like this. And so then we say, okay, my triple bond used to be right here. So the alkyne that formed this would have looked something like this. And again, numbering your carbons. So 1, 2, 3, 4, 1, 2, 3, 4. Okay? And then I say, okay, so can I go from my beginning alkyne to this alkyne? The answer is yes. Through an acetylide ion reaction, we can go from this beginning alkyne to this alkyne we're looking for. And we found that out by going backwards from our product called retrosynthetic analysis. Okay? Honestly, whichever way feels most comfortable for you, whether it be retrosynthetic analysis, just going forward, whatever, I tend to do a combination of the two. What I tend to do is I say, okay, if I take one step back from my product, can I get there from my reactant? If not, I'll take another step back. Can I make it there from my reactant? Then I'll put everything into motion. So that means for this reaction, I would want to start with, so I'm going to erase this middle arrow here so I can just sort of draw out the different reagents. So I'm going to start with what? Oh, I'm going to need to make an acetylide ion. So I'm going to start with NaH, NaNH2, organolithium, anything to make my acetylide ion. So I make my acetylide ion. Then I say, okay, how many carbons do I need to add there? Oh, I need to add 2 carbons. So I'm going to react this with a 2-carbon chain with a good leaving group. What that means is we're going to replace that leaving group with our carbon chain, our acetylide here. And then that creates this guy right here, which then the reagent that we use to create this into a terminal enol is we use either RBH, RBH2, BH3, whatever. RBH, anything with boron, H2O2, and OH, 1, 2. And then we just undergo tautomerization. Okay? Does that sort of clear up some ideas about synthesis that you were having trouble with? Okay. So again, synthesis is sort of a hard thing to do. It's a hard thing to sort of wrap your brain around. But again, really knowing all of your reactions, all your reagents will help you a lot. And I'm going to give you the advice of doing a whole bunch of synthesis questions. Even if you don't know the reactions by heart, if you start doing synthesis questions, if you start putting it into practice, it'll make it way easier uh, if you it'll make it way easier to understand each reaction and what they do. And going from the alkyne to the pink arrow, essentially what we did is we turned it into a really strong nucleophile by deprotonating it into a negatively charged acetylide ion. And then what did we do? We just did an SN2 reaction with an alkyl chloride, which happened to have the correct number of carbons, to make this alkyne right here, which then underwent hydroboration oxidation, which then underwent tautomerization to create our final product. Do you recommend doing the synthesis? I recommend doing any synthesis questions that you can find. Doing the synthesis questions from the book will probably be easiest for you because you probably have the solution manual already. Whereas if you Google it online, those synthesis questions may not be the easiest one thing. They may be reaching for concepts you don't know yet. And using the book, you're going along with what they're teaching you. They're not going to expect you to know something that they haven't taught you yet, et cetera, et cetera. So I recommend going with the book rather than looking up questions online. All right. And I think that is about it for this review. I hope I helped out. Yes, we did not go 3 hours this time. Yay! But yeah, so just let me know if you have any additional questions in the comments below, et cetera, et cetera. In the group me, in Discord, whatever, just message me and I'll answer any of your questions as soon as possible. All right? See you next time.